Hey everybody, this is a little bit later than I intended, but this is the kind of wrap up of day 4 where we finished up our chapter on sugars. I'm going to use a few slides here to talk about some of the key points from that lecture. So one very important skill for this class, and one thing that I've been asked quite a few times about, is specifically about anomeric carbons and identifying anomeric carbons. One of the questions that I get on a regular basis is, does a linear form of a sugar have an anomeric carbon, or some variation of that question? What I'm going to do is I'm going to go ahead and draw glucose. So I'm going to draw D-glucose. So my penultimate carbon, carbon number 5, has a hydroxide group on the right-hand side. 4, it's on the right-hand side. 3, it's on the left-hand side. 2, it's on the right-hand side. And number 1 is my aldehyde, so it has but 1 hydrogen and 1 oxygen, so it is attached to 3 groups. So what's important for you to do whenever you're looking at different sugars is to be able to identify chiral centers. So if we look, we've got 1, 2, 3, 4 stereocenters or chiral centers when we look at our linear form of glucose. Then, whenever we cyclize glucose, we have CH2OH. OH, and OH. Okay, now if we count up our chiral centers, looking at carbon number 1, that's where we can immediately see the difference. Carbon number 1 is attached to how many different groups? This carbon has a hydrogen, it's linked into the ring through a carbon, it's linked into the ring through an oxygen, and then a hydroxyl group. So this has a total of 4 different groups attached to it, 4 different unique groups, compared to carbon number 1 in the linear form, where we only had 3 different things that it was attached to. So carbon number 1 immediately jumps off the page. Carbons number 2, 3, 4, and 5, there is no difference between those. However, those were chiral centers previously. So carbons 2 through 5, C2 through C5, are basically unchanged. Whereas carbon number 1 is now a chiral center. So whenever you think about anomeric carbons, one of the things that you have to think about is the definition, and the definition is a newly formed chiral center. So carbon number 1 is your anomeric carbon whenever you're talking about an aldose, and carbon number 2 whenever you're talking about a ketose, because both of those were not chiral centers, and whenever you have the cyclized form of sugar, they are. So aldose and ketose. Alright, so next up we're going to move on to talk about disaccharides. Right here I have a total of 3 different disaccharides, and all 3 of these disaccharides involve D-glucose. Okay, so the first disaccharide is maltose. Below that is sucrose. And to the right is trehalose. Now, when you look at all of these, what I want you to see is the sugar on the left, here, here, and here. I want you to be able to easily identify those as glucose. Now, the way that you're going to present this, what I also want you to do is look at the anomeric carbon of that glucose, here, here, and here. So these are all the hydroxide groups on this glucose that are looking at these anomeric carbons. These are all alpha sugars. What I want you to do is label these accordingly. So if you're coming up with this name, you will first write out alpha, because all of these are alpha sugars. In the event that you're working with a beta sugar and a disaccharide, then you'd write out beta. So this is an alpha sugar. All of these are also D sugars. So alpha D, and then what we're going to do is we're going to write glucose but use a different suffix. We are going to call this glucopyranosyl. So that pyrano, that's indicating that this is the pyranose form of that sugar. So alpha D-glucopyranosyl, and then for the case of maltose, what we're going to do is we're going to write in, actually for all of them, we're going to write 1 dash. Okay, so this is a common part for all of these disaccharides. Now, we're going to specifically hone in on maltose. So I'm going to go ahead and circle this to say that we are only talking about maltose from this point forward. What we need to do is show where our bond goes. So our sugar to the right, or on the right-hand side of our molecule, is, well, as it turns out, it is also glucose. Now the linkage between our two different sugars that make up this disaccharide, this is an O-glycosidic linkage. Now with that said, I clarify O-glycosidic because there are also N-glycosidic linkages, and you want to take a wild guess. Do you think that they include nitrogen? Absolutely, they do. Okay, so an O-glycosidic linkage. We have that O-glycosidic linkage between carbon number 1 and carbon number, if we look at our sugar on the right-hand side, 1, 2, 3, 4. 1-4. So 1, 4. Now, we have to identify this other sugar. Well, looking at carbons 2, 3, and 4, we have down, up, down. Well, what do we know about glucose? Glucose is down, up, down. We're going to also look at carbon number 1. Is this sugar also in alpha form? Yes, it is. So we could go ahead and write alpha. This is also a D sugar. Alpha D glucopyrano. We're going to use a different suffix though, pyranoside. Okay. So this is alpha D-glucopyranosyl 1-4 alpha D-glucopyranoside. Now, if we look at trehalose off to the right here, one of the things that I want you to really recognize is that this sugar looks quite a bit different. Now, let's try to identify where our anomeric carbons are. Well, we already identified our anomeric carbon for our glucose on the left. Now, what are we looking for whenever we're looking for an anomeric carbon? Well, we want to find where the oxygen that is within our ring is, and then find adjacent carbons. Well, this adjacent carbon right here has a hydroxide group. Lo and behold, that would be our anomeric carbon. Okay, so we have an anomeric carbon there. Now, this is a different representation than we've looked at for other sugars because of the fact that, well, our oxygen within the ring is below. Okay. Now, I don't want you to stress too much about this structure right here, but what I want you to recognize is we have carbon number 1, 2, 3, 4, 5, and 6. So this is a hexose, and I'll just go ahead and let you know that this is also a D-glucose molecule. Now, what we're looking at here is another disaccharide of glucose. The fundamental difference between these two molecules is, well, we have a linkage that is 1 to 1. Okay, so the anomeric carbon of one glucose links to the anomeric carbon of the other through an O-glycosidic linkage. So does this have a free anomeric carbon? The answer to that question is no. When you compare that to, well, maltose, does maltose have a free anomeric carbon? So is that anomeric carbon, or is one of the anomeric carbons on maltose freely accessible to be involved in any other sort of future chemistry? The answer there is yes. So whenever you have a sugar that has a free anomeric carbon, or a sugar that does not have a free anomeric carbon, we use the term, we identify a sugar as a reducing sugar or a non-reducing sugar. Maltose is a reducing sugar. Trehalose is a non-reducing sugar. Along those same lines, when you look at something like sucrose, okay, well, I'll task you with identifying where your anomeric carbons are. We already know that this is a D sugar and it's glucose on the left-hand side, so there's our anomeric carbon glucose molecule. Then we have our glycosidic linkage. Remember, we have a 5-membered ring here. We're looking for our oxygen that's involved in the ring, the carbon attached to it. Does that have a hydroxide group? This one does. Therefore, that is our anomeric carbon. So our lowest possible number for that would be carbon number 1, 2, 3, 4, 5, and 6. This is fructose. Now, if you were describing this bond between these two, well, this is a 1-2 linkage. Now, glucose happens to be in the alpha, whereas fructose is a beta sugar in this case. So that's significant whenever it comes to writing out the full names for those, but ask yourself, is sucrose in reducing or non-reducing? And that question can be simply addressed by, does it have a free anomeric carbon? Yes or no? Well, fructose, no free anomeric carbon, therefore it is a non-reducing sugar. So, we did in lecture go beyond this, and we talked a little bit about polysaccharides. We talked about glycogen linkages that exist between different glucose monomers in glycogen molecules, as well as cellulose. So take a look at the notes that I posted on Tracks, the handwritten notes, as well as the PowerPoint presentation. But that ought to do it. I will see you in lecture.